Hello and welcome back to Advent of Code 2016, day 15. Um, so, yep, we're in the end game now. We're like halfway, just over halfway. Okay. All right, let's do this. So last time we had some nice problems. They were mostly breadth first search, I think, but and then the last one was like MD5 hashing, which seems to be common throughout this year's puzzles. Timing is everything. Alright. Let's read. The halls open into an interior plaza containing a large kinetic sculpture. What's a kinetic sculpture? Sculpture is in a sealed enclosure and seems to involve a set of identical spherical capsules that are carried to the top. Oh, it's moving sculpture. Okay. Carried to the top and allowed to bounce through the maze of spinning pieces. Damn it. Hang on. Part of the sculpture is even interactive. When a button is pressed, a capsule is dropped, and tries to fall through slots in a set of rotating discs to finally go through a little hole at the bottom and come out of the sculpture. Oh my god. Okay. Why is it? Fascinating. Okay. Part of the sculpture is even interactive. No, I already read this bit. No, I didn't. When a button is pressed, a capsule is dropped and tries to fall through slots in a set of rotating discs to finally go through a little hole at the bottom and come out of the sculpture. If any of the slots aren't aligned with this capsule as it passes, the capsule bounces off the disc and soars away. You feel compelled to get one of these capsules. The discs pause their motion each second and come in different sizes. They seem to each have a fixed number of positions at which they stop. You decide to call... Hello, DJ. It's going alright? On day 15. Seems to be a sort of physics-based simulation. Well, we'll see. So, we've got balls falling through a sculpture. They seem to each have a fixed number of positions at which they stop. You decide to call the position with the slot 0 and count up for each position it reaches next. With the slot. So if the disc is rotated into position 0, then the ball can actually fall through. Any other position, it will just bounce off. Okay. Furthermore, the discs are spaced out so that after you push the button, 1 second elapses before the first disc is reached. And 1 second elapses as the capsule passes from one disc to the one below it. So if you push the button at time t equals 100, then the capsule reaches the top disc at time equals 101. The second at 102, it's okay. The button will only drop a capsule at an integer time, no fractional seconds allowed, okay? For example, at time 0, suppose you see the following arrangement. Disk 1 has 5 positions, and it starts at 4. Disk 2 has 2 positions, and it starts at 1. Why Why do they need to specify time equals 0? Can it start at different times? Let's have a look at the input. No, it's always time equals 0. There's only 6 disks. Interesting. Okay. So in this example, if you press the button exactly at time 0, capsule would start to fall. It would reach the first disk at time equals 1. Since the first disk was at position 4 at time equals... Okay, fine. So 1 ball gets spent to switch it to 0. Disk 1 will be in position 0, and then the ball will fall through at time equals 1. Reach the second disk, and now the second disk has to flip up to 2 and then to 0. Okay, I get it. Oh, I thought the ball was causing these disks to move. No. They are rotating every second. Interesting. So you need them all to be lined up. Not lined up, but lined up according to their time. Interesting. So you want to find the time to drop the ball. So time equals 5 is when you drop the ball. So you're trying to work out where disk 1 is at 0. Disk 2 is at, let's say, -1 to mean 1 before 0. Disk 3 is at -2. Disk 4 is at -4, and so on. The time at which that happens is precisely the time at which you press the button, right? Okay. Why do I feel like this might be the Chinese remainder theorem or something like that? What is the Chinese remainder theorem? Man, it's been decades since I've been in school. Let's see. No, it's not the Chinese remainder theorem. It's just standard lowest common multiple, isn't it? Yeah, no. The Chinese remainder theorem is a bit more complicated. No, we're just trying to... Right, let's just have a look at this. Okay, fine. Oh, we don't need to... We can just copy this. We can just write this in directly. Interesting. So we're trying to find... time t, which satisfies 6 modular arithmetic equations. It's not Chinese remainder theorem. What is it? It's something... God, it's been... number theory. We could just solve this by ticking up. I don't think it's even going to be a long time. But I'm trying to think what the... You're trying to solve 6... I think it is Chinese remainder theorem. Let me type this out again. Yes, it is. The first time I read this, I read that first paragraph and I was like, no, that doesn't fit this. It does fit it. We know the remainder by several integers. Yes, we do. That's what's given us in the input. One can determine uniquely the remainder of the division by the product of these integers. And if we know that, then we just have to count up in the products of the integers. I'm pretty sure you don't need the Chinese remainder theorem to solve it, but I'm gonna solve it using the Chinese remainder theorem because that's actually seems quite interesting. I'm guessing you can just kind of do a similar thing from first principle and get the solution that way. All right, so let's try and use the Chinese remainder theorem. So we know, yeah, this is what we know. We know if the ni are pairwise coprime, is that the case? Yes, they did this on purpose. 7, 13, 3, 5, 17, 19. They did this on purpose. They want us to use the Chinese remainder theorem. Or at least the smart ones amongst us. And if a to 1 to ak are integers such that they are all... Yeah, that is the case. Yes. So we need to rewrite it in terms of this. X equals a1 mod n1. In the, for example, the first one would be so disk 1, so it would be t equals 0 mod 7. That means the time at which we drop it must be 0 mod 7. So every 7 we're allowed to drop it, and 0 is the first time we're allowed to drop it. So that's clock maths. All right, so and then disk 2 would be -1 mod 13. And -1 is 13, is 12. Okay, so disk 2, t equals 12. Okay, let's actually write this into the editor. Okay, so this is interesting. It's like I'm back in school. Okay, so so we need A1. Okay, let's just copy this in for now. Okay, so this gives us A1 equals 0, and then the n value, n1 equals 7. Let's just put these on the same line. A1 n1 equals 0 7. A2 n2 equals and we could do this for lots of them, but okay, so it's gonna be, so these numbers are the A numbers, but you gotta subtract 1, then 2, then 3, and so on. So A2 would be 12, 13. A3 n3 equals, so it'll be 2 minus 2, so 0, 3. A4, oops. So let's make this a bit bigger. A4 n4 equals 2 minus 3, so it'll be 4. Five. A5 and 5 equals -4, so 13, 17. A6N6 equals so -5, so 2, 19. Okay, that's the data we need. So we're trying to solve those 6 equations. So the theorem says okay, so we let n equal, so n equals the n equals the product of all these n values. So n1 times n2 times n3 times n4 times n5. This is the benefit of using Python, big numbers. N6. Okay, what next? Okay, the wiki's not very clear on what to do. It just gives lots of different methods, but it's a lot of, it's very wordy. Hang on. Computation, here we go. I'm just kind of reading this. I think most of this is not important. It's just proving that it works. Where do we actually get to the computation? Okay, here we go. Systematic search. Oh. I mean, the first method is saying just try all values, so we didn't need to use anything. We could have just tried integers. Okay, I get it. So we can either use... Oh, I probably should have showed this wiki on stream. This is probably really boring, me just staring at the thing. Okay, fine. Well, we can just try brute forcing, but there is algebraic methods, but it uses a matrix, so... Oh, there's sieves. Sieves are actually reasonably easy to write. A sieve... Oh, I remember this from school, actually, so long ago. Never really understood it back then. All right, let's just do brute force. Okay, so, and if that doesn't work, I'll move on to the sieve. So, basically, there is a unique value from 0 to n, well actually n minus 1, which satisfies these 6 equations. So we can define is solution x. So x is a solution if return let's say t, return t equals t percent n1 is a1 and t percent n2 equals a2 and t percent n3. I suppose they wouldn't really expect you to know the Chinese remainder theorem, but if you do, that probably helps you if you're able to code these matrix methods quickly. But I think this is actually probably just solvable by brute force. The hard bit in this question is really just unpacking what they're trying to say here. Okay, there's a smarter way to do this. Return all... No, let's just carry on. We're almost there. Because I haven't enumerated these, so... t percent n5 equals a5 and t percent n6 equals a6. Alright. For t in range n. You see if ChatGPT does it the smart way. Maybe, yeah. I mean, I'm looking at... Okay, the sieve method doesn't look that complex. It's just, you wouldn't... I'm gonna just... It just takes longer to code, so I'll just do this. All right, for t in range n, if is solution t print t break. Let's print n. I want to see what kind of number we're dealing with here. It's not... It'd be quite big, but it's not... It's going to be like a order of 1,000,000 or something. That's not actually that much, so we're fine, really. Okay, it was instant. It was completely instant. There's absolutely no reason to use the matrix or sieve methods. Well, let's see if it's correct. 264159. Yeah, because it's only 6 numbers, so that's going to be 1,000,000 or so. You did not need to even know the Chinese remainder theorem. It would have been faster if I just didn't know about the Chinese remainder theorem, then I wouldn't look it up. All right. The Chinese remainder theorem is useful if you had a lot more to deal with. It's not right. It's wrong. Okay, have I unpacked this all correctly? So... Okay. Have I... Oh, wait, why am I minusing? It should be plussing. Hang on, let me go back to this. So... it should be... So why am I saying it should be 12 mod 13? Because at time t equals 1... t equals... I think it's the other way around. It should be 1. Because... No, it is 12. So if we would just ignore the last 4. If t was 12, for example, which is 12 mod 13, then at time t equals 0, you drop the ball, it'll go past the first one, whatever happens, we don't care. And then 1 second later, this will be at 13 mod 13, which is 0. So it'll be able to go through. Yeah, no, so I've done it right. I've written it out right. I should probably put the exact input in just so I can refer to it. Let's see. So, okay, so the n values are 7, 13, 3, 5, 17, 19. The a values, there's a cleaner way of doing this. Let's just write out a equals n equals. Okay, so n values are 7, 13, 3, 5, 17, 19. A values are 0, I need to think a second. Okay, fine. Yeah, so 0, 12. So I said 0 for the next one. Is that correct? So if it was 0, if disk 3 was 0, t was 0 mod 3. i.e. a multiple of 3. Well, at time 0, it's at 2. At time 1, it's at 0. At time 2, it's at 1. Time 3, it's at 2. Okay. So if we drop it, it's at 2. It gets to disk 2, and it's at 3. And it gets to disk 3, it's at 1. Oh, I'm getting so confused with these numbers. Maybe I need to do a diagram. So t plus 2. At time t plus 2, we need it to be at 0. I can't reason this out. This is not hard, but it's just converting these words into numbers. It's confusing me so much. All right, start from scratch. Okay, so we've got a disk. It starts at position 2. So every second, at time t, it's at position t plus 2 mod 3. It's at position t plus 2. At time t, it's at t plus 2. At time t plus 1, it's at t plus 3. At time t plus 2, it's at t plus 4. So we need t plus 4 to be 0. So what you need is t plus the number of rows we need to go down, i.e. the number of seconds it takes to fall to that point, plus the number here needs to be 0. Okay, so t plus 4 is 0, so t equals minus those two things, minus 4. 3 minus 4 is minus 1, which is 2. So that should be 2. Okay, let's do that for each row. Okay, so you do so row 0, it's row 0 and that's 0. So you do minus 0, minus 0. So it's 0. That's a 0. Okay. Row 1. It's row 1, position 0. So minus 1. So 12. Correct. Row 2. Minus 2, minus 2. 3 minus 2 is minus 1. The 3 minus 4 is minus 1, which is equivalent to 3. 2. Okay. Row 4. Minus 3, minus 2. So 0. I've got all these numbers wrong. Okay, 5. So we do minus 4. So 17 minus 4 is 13. Okay, and then finally 6. We do minus 5, minus 7. So that's minus 12 altogether. 19 minus 12 is 7. So that should be 7. All right, let's try that then. One, 2, 1, 8, 3, 5. Smaller, so that's a step in the right direction. Not right? It's too high still? Okay, fine. I think I'm getting closer to understanding this. I was hesitant to write things down on paper because then you can't see what I'm writing. I could write here, but fine. I feel like that's still a step in the right direction. That thinking now, just go work out what I did wrong. All right, let's write this all out. We don't need to manually do stuff. Let's say positions. Hang on. Positions equals 7, 13, 3, 5, 17, 19. Initial pause equals 0, 0, 2, 2, 0, 7. So the n value is just the positions. All right. In fact, we should probably just call that n. The a value is let's say the index. Let's say the index is I. So the disk 1 is index 0, disk 2 is index 1, and so on. So that's how many seconds it takes to get to that disk. Okay, so we've got t, the time we drop the ball. T plus I. That is the time at which the ball reaches your disc. Plus the initial position that will give us the new position we're at by the time the ball reaches us. And we want that to be 0 because that's the only time the ball's allowed to go through. So we say equals 0. So it's standard algebra. T equals minus index minus initial position, right? So A equals minus I minus initial position I, or I in range, say length of n. But we need to modulo n the n value so that it falls between 0 to n minus 1. Alright, so let's print what A looks like. Don't do any of... Okay, take this out. Zero 12 2 0 13 7. Does that match what we had before? 0 12 2 0 13 7. Okay, fine. That does match. Now what? Okay, so this doesn't actually matter, this n thing, but okay, we can do it anyway. N, let's say capital N equals product? Is that a thing in Python? Itiples? No, I don't think this is what we want. Okay, just do map. Map and map. No, it's map. Map produce. I can't remember how to do this. Alright, just say n equals 1 or x in n multiply equal x. So now that's the product. Print n. Alright, define is solution. Return all all t equal t percent n is n I is equivalent to a I or I in range length of n. And then for t in range capital N, if it is a solution, print t break. This is roughly what I had before. All right, take this out. I'll leave it in. 121835. That's the same. Fine. Let's try the example they gave. So we had example disk 1 That's 5 positions, disk 2. So that would be... Uh, 5, 2. Initial position would be 4, 1. So it says 6. And what is the answer to this? It says time equals 5. Are we 1 above? 1 off? Oh, bollocks. You don't drop the ball at the first disc. It takes 1 second until it reaches the first disc. Yeah, that's the problem. That makes sense. Of course the ball's going to fall a bit before it reaches the first disc. Okay, so we're 1 off. Alright, fine. That was the issue. I don't know, keep that just in case. Yeah, I've just read the description now. Alright, go back to this. So just need to say... So the N was correct. Initial position is correct. So we need just to add 1. Minus 1 because it's the other side of the equation. Let's try this with the example. Five. All right. That's correct for the example. Yeah, that's what I get for not reading this description correctly. 1, 2, 1, 8, 3, 4. So we were too high before. We were 1 above, probably. All right. Correct. I definitely overcomplicated that. I think worrying about the Chinese remainder theorem definitely slowed me down. If I just never knew about the Chinese remainder theorem and just approached this logically, drawing a diagram as well, that I think I would have got there faster. You just set up the algebraic equations for when it reaches each point. Throw in some modulo arithmetic. Modular arithmetic is something that not everyone knows, though, but it's very useful. All right, part 2. After getting the first capsule, it contained a star. Well, great fortune. The machine detects your success and begins to rearrange itself. When it's done, the disks are back in their original configuration as if it were time equals 0 again, but a new disk with 11 positions and starting at position 0 has appeared exactly 1 second below the previously bottom disk. So they're adding a new disk, so this is going to increase the complexity tenfold. So we only have to wait 10 times as long, in theory. Right then. Which should be fine. It was practically instant. Alright, so we've got just copy all this. Just copy the whole lot. Yeah, I mean, when I was in school, modulo arithmetic was not something that we were really taught, but it was something that we learned on the side because we were taking part in competitions and stuff, and it was needed for those. The Maths Olympiad, BMO, and International Olympiad, if you were to get that far, which I never was. it used a lot of modular arithmetic. I think in my final year of school we did actually learn modular arithmetic properly. But the questions were really easy because a lot of us had already learned it for BMO, so... Paste all this. So it's the same as before, but you just add 11. And it says... starting at position 0. Okay. So you just add a 0 here. Alright, let's stop printing this stuff. Alright, it's going to take 10 times as long. Oh, there we go. 3208099. Should work. It's just adding a disk. Correct. Alright, now let's watch ChatGPT destroy me. I think you'll be able to solve this, because there's probably a lot of people who have done Chinese remainder theorem questions for ChatGPT in the past. That is an absurd amount of seconds you have to wait to press a button, yeah. But yeah, it just goes to show the combinatorial explosion. If all you need to set up is 11 disks such that they're co-primed to each other in terms of how many positions they have. And then it takes order of millions iterations before they all line up, but that's what you'd expect. If they weren't co-primed to each other, then you would have repeats, so you wouldn't have to wait as long. But if they're co-primed to each other, and not only are these co-primed, but they're actually prime numbers as well, so they're like fully prime, then there's only a unique lining up within the first capital N iterations. Okay, it's time to consult. Oh, they need to make a dark mode for ChatGPT. Paste in the problem, but I'll paste in the input as well, because it's a small input. All right, let's see. Solve disks. Oh, he's actually simulating it fully. He's not using modular arithmetic. He's just saying, this is where they are at time t equals 0. I mean, that's actually the same complexity, isn't it? Because I didn't end up using anything smart. So actually, if you didn't know about modular arithmetic, that's actually probably easier to code than what I did, to be honest. Just literally put all the disks at their starting points, and at each tick just increment them. I mean, technically it takes 6 times longer than what I did, because you are... No, it doesn't. It takes the same complexity as what I did. Yeah. So yeah, you just keep ticking them up by 1 each until you see them all at 0. Yeah, I mean, that's I should have really just done that from the start. Alright, let's test this. Yeah, because then you didn't have to faff about with computing what the A value was, which stumped me at first, and I got it wrong the first time, so 121834, that's correct. He's definitely beat me there. And that's that. I would say his code is better too. I mean, it's more readable, definitely. And writing it this way round is smarter than what I do with the minuses. The minuses just... that just makes it look confusing. Also didn't have to -1 its answer. Well, I didn't have to either. The -1 came in the equation. I didn't put a -1 at the end. I could have, and that would have got me the same answer, but I put it into the equation, so it's actually equivalent to what he's done. He's got the 1. Oh no, he doesn't need a 1 because of the way he's enumerating this. But yeah, it's equivalent. But this is just more readable than what I did. I did it backwards, -I. You would only understand that if you understood the algebra I wrote before, but then I deleted that. That was in the comment. Yeah, ChatGPT is just better, as always. Alright, part 2. He shouldn't have any problem with this. Now adjust for the following. Is it worth testing part 2? Because all you do is add 2 numbers with no code changes. Well, we'll see if he does it correctly. But yeah, I mean, almost certainly he will manage, but we gotta prove it. Now adjust for the following modification. Yeah, he's even commented at new disk. He's reduced the variables to letters. That's probably better. Whoa, look how compact that code is now. He's changed it. Solve used to look like this. Now it looks like this. Oh, because he's using itertools count. What is count? Does it count infinitely? Infinitely. Oh. Oh, I'm doing that next time. You don't need to make infinite loops where you increment I in an index each time, and then at the end you have to remember to add 1, which is what he's doing up here. I hate doing that, because I'm always worried I might forget to add 1. There, so this is time equals 0, and then he's adding 1 each time. But if you use count, then you just do for t equals count in count, and that's safe. You never have to worry about whether you're adding 1 or not, which sometimes if you change the code in here, you might accidentally remove that or comment it or something. Oh man. Learning new things. I'm definitely using that from now on. And it will just keep incrementing infinitely until you break out. Cool. I need to have a proper look at ITA tools. There's probably so many things in there I'm not using that I should be using. Alright, let's just test it and get this over and done with. Press button at time. Yeah, okay. Yep. So that's another win for ChatGPT. I've got a little scoreboard here. Put my head in front of the light bit of the window. All right then. $16. Dragon checksum. Modified dragon curve. This looks interesting. Oh, it's some sort of encoding. Oh, they really love their encoding and cryptography in this year, don't they? Yesterday there was a pretty complex one involving MD5 hashes. That's the one that ChatGPT failed. Okay. You're done scanning this part of the network, but you've left traces of your presence. You need to overwrite some disks with random-looking data to cover your tracks and update the local security system with a new checksum for those disks. Okay. For the data to not be suspicious, it needs to have certain properties. Purely random data will be detected as tampering. To generate appropriate random data, you'll need to use a modified dragon curve. I mean, I've studied fractals before, but I've never heard of a dragon curve. Oh, it appeared in Jurassic Park, my all-time favorite book. I don't even remember that. It has been a long time since I read it. I've got to read it again. That's what the curve looks like. Yeah, fractals are... I mean, they're really cool, but they also don't really have a use. I think mathematicians just study them for fun. But you're not really going to get funding to research this stuff in depth normally. Maybe they have a use, some uses, but I think that it's more almost recreational mathematics. Dragon. Dragon. Hayway dragon. Harter Hayway dragon. Or the Jurassic Park dragon. I think I prefer the Jurassic Park dragon. Was first investigated by NASA physicists. Okay, cool. Start with an appropriate initial state, your puzzle input. Oh, okay, that is our puzzle input, right? Then so long as you don't have enough data yet to fill the disk, repeat the following steps. Call the data you have at this point A. Make a copy of A, call this copy B. Reverse the order of the characters in B. In B, replace all instances of 0 with 1 and all 1s with 0. Okay. So B is reversed and inverted, sort of. The resulting data is A, then a single 0, then B. Okay. I mean, this is just begging for Python, isn't it? Python is just the best at handling strings. String manipulations, reversing, inverting, all this stuff. Apparently, fractals are used in cancer diagnosis and image compression resolution. Actually, yeah. Okay, image compression and resolution, that makes sense. Sort of. Because it's always... image compression is often about identifying redundant patterns in images and compressing those patterns. Cancer diagnosis? Okay, I don't know how they're used in cancer diagnosis, but that's interesting. Can't think how they would be used. Human cells grow in a fractal patterns, cancer cells do not. Ah. Actually, yeah, that's the point. Fractals aren't just something we made up. They do actually occur in nature. I mean, the Da Vinci Code had a whole chapter talking about fractals, I think, and how they are in like cauliflower. There's that cauliflower which is shaped like a fractal, and hello, Mugurelius. It will be able to in the future. ChatGPT 5 will change everything. What? So this is what, ChatGPT 4? Yeah, I mean, they're already looking into, and it's not even a new thing. They have been looking into using these AIs to diagnose diseases for many years now, but it's getting better at it, definitely. Like they test that these chatbots are able to pass like medical exams that med students take. Free version is 3.5, 4 is plus version, 5 will be launched, and people will say, okay, that will never outperform a doctor, but then if you look at all these third world countries that can't afford doctors, this is a fantastic solution. 100 quadrillion parameters, or perhaps more. Yeah. Yeah, we're making history. We will be outperformed as humans, but we should be thankful. Mass Effect's time's coming. Yeah, I mean, years ago when people were worried about robots taking over our jobs, I was always like, don't worry, we programmers will be the last people whose jobs will be taken over by the robots because we're the ones that will program them. But, I mean, I'm just proving now that programmers are soon to go too. .5 has 100 billion parameters, 4 has like 100 trillion. Okay. Every guy out there is scared for AI and shit. Still, it can help us. Yeah, I'm all for it. Like, you know, people had the same reservations about the internet. And a lot of people did lose jobs because of the internet. It was a revolution and lots of people were out of jobs. And, you know, shops had to close down and stuff. But it's definitely been a progress. Funnily enough, enough manual labor jobs are complex enough, robots can't do them, but they can easily do brain stuff. But they can... What do you mean by brain stuff? Oh, you mean like kind of like academic, professional stuff? Yeah. I mean, people are proving that it can even be creative. It can write comedy scripts and soap opera scripts and all this kind of stuff. I'll graduate college in 1 month as engineer, you can imagine. Yep. Just, I mean, the best security you can have is, I guess, getting into AI as part of your degree, or at least taking a course in it, at the very least, or something like that. I mean, that's kind of what I'm doing is now. In fact, when was it? January. Yeah, I taught a course in a postgraduate university in Saudi Arabia in this January for 1 week on how to use AI to play games. They flew me in. They flew me there to teach the course. It's pretty good, but I mean, I had applied to teach a course there before, but I was always rejected. Only when I made it about AI did they accept it. So, you know, AI is the hot thing right now. Before I made it about like some generic programming stuff, and they were like, boring. You just gotta add the buzzwords. AI, machine learning. Alright, I've gotta finish reading this. Okay, so it's A0B. Okay. I get that. And that seems pretty easy to program, unless they want it... I can't think of any clever tricks here. I think just program it exactly as they've worded it. Normally with fractals, there's no shortcut to finding the distant fractal. You just got to actually do the iteration step by step. Repeat these steps once the data has been generated. Okay, once the data has been generated, you also need to create a checksum of that data. Calculate the checksum only for the data that fits on the disk, even if you generated more data than that in the previous step. Okay, fine. Considering each non-overlapping... Huh? Each non-overlapping pair of characters in the input data. If the two characters match 00 or 11... Oh, okay. I didn't understand that at first. Okay. That's a weird way to word it. Non-overlapping... Oh, no. Oh, I see. Non-overlapping pair means 0 and 1, 2 and 3, 4 and 5. Okay, that's what they mean. Okay. So you take each pair, each disjoint pair of characters, and if they're the same, it's a 1. And if it's not, it's a 0. And that compresses it by a factor of 2, essentially. Okay. Exactly as half as long as the original. Yes. If the length of the checksum is even, repeat the process until you end up with a checksum with an odd length. Okay. Yeah, okay, I don't even need to read the example. I think that's pretty straightforward. Alright, so just gotta code this all. So that's our input. So 16. So input. No, what did they call it? They called it just initial state or data or whatever. Data equals make this a list. Lists we can append. And right, so that will just be the list of well, let's use integers, not characters. So list of int character for character in okay, and then we've got disk space 272. Okay, excuse me. All right, those are the two values they've given us. All right, so while length of data is strictly less than 272. So we keep fractalizing this until it's greater than 272, greater or equal to 272. So let's go through the steps. We have data. We call it A. So we go okay, we okay, L equals length of data. We need to know the length because we're going to manipulate this. So first let's put in the 0, data dot append, because you need a 0 in there. So there's a 0, put that after there, and then you put the inverted reversed thing afterwards. So for I in range starting from L minus 1 and going backwards until we hit 0. Data dot append. Ooh, are we allowed to do this? It might complain because we're manipulating data while iterating over it. It's a bit naughty. All right, data dot append. Oh no, but we're not iterating over it. It'll be fine because we're iterating over just a range, an arbitrary range. Okay, data dot append data. So we have to invert it. 1 minus data I. So we go from the end of data backwards. Hello, rabbits. Thanks for the follow. Are you familiar with Advent of Code? or Python programming in general, or ChatGPT. So data.append 1 minus. So that's it. If we do this, we'll end up with our data. Let's see what it looks like. That's our data. That's the fractal. It starts off looking exactly like the data, but it's reversed and inverted. Okay, next step. We need to find the checksum. So we don't need the data for anything now, so we can actually just use data to hold the checksum. The checksum initially is just the data. Oh, we have to discard some characters, so we have to discard. All right, let's make a copy here. Checksum equals data up to disk. So we discard everything after 272. Okay. While you like to watch a programming stream. Nice. If you don't know what this is, basically we're trying to solve advent of code problems, which are every December, shortly before Christmas, this guy called Eric Wastel makes these problems and releases one each day until the 25th. It's really fun. They start off quite easy and then they can get difficult at times. They're all programming related, but they're kind of mathsy puzzles, usually involving like searching through a graph or a grid of something, or sometimes more complex stuff. This problem here is kind of about making a fractal, which is like these visual things, but it's not a visual fractal. It's just involving zeros and ones. So we're just trying to follow this process step by step. There's no trick to this. There's no clever algorithm. I think literally just follow these steps and we'll get the answer. So I'm at this bit here. So if the length of the checksum is even, repeat until it's odd. Okay, fine. So while hang on, switch back. While length of checksum %2 is 0. So keep compressing it until it's got an odd length. All right. So new checksum equals, just make a new one. For I in range, so we need to go from starting from 0. Skip every second character. So I and I plus 1 will be the next pair to deal with. New checksum dot append. So we basically want the bit, what is it called? The XOR value. It's no. What did it say? If they're the same, we put a 1. If they're different, okay. So it's basically int of the truth value checksum I is the same as checksum I plus 1. So if they are, that'll be a true, which will turn into an int, which is a 1. Otherwise it'll be 0. And now just swap checksum equals new checksum. All right. Now what? Just print checksum. So it should be, what's 272 divided by 2? 136. What's that divided by 2? 68. What's that divided by 2? 34. 17. Okay, so it should be 17 characters long. Oh, print. We need to join it up. Print dot join. Map it to a string. There we go. Alright, soon we'll get to see ChatGPT solve this faster than me. Correct. Part 2. The second disk you have to fill has length that. Okay. Do we just do the same thing, or is there going to be a catch here? So that is now the length. Let's do this all again. Also, that should use the variable. Just start the whole thing again. So change that to be that. So that's 35 million. So we're doubling its size until we get to 35 million. So that's gonna that's not gonna take long. And then we're halving it again until it becomes small again. It's fine. It's not gonna take that long. It'll be linear in terms of million, because if you add 35 million plus half of it, plus half of that, plus half of that, you end up with just 2 times the original number. It's like 1 plus a half plus a quarter plus an eighth plus a 16th and so on equals 2. So at most we're going to do like 7 million steps, I think. So it should just be really fast, right? Maybe not really fast, but it should be reasonably fast. I mean, we're getting close to 1 billion here, but it's still not okay. There we go. once you're in the billions, then it takes too long. But we were just, I don't know, 500 million. Done. All right, now let's watch ChatGPT solve this. So we need to say, can you write a Python program to solve the following problem? Oh, not this one. We need to tell it what the input is as well, which is just that. All right. Dragon curve, checksum. Well, he's laid it out really neatly. That's so much cleaner than what I did. Okay, he's working with characters, string characters. I prefer integers because then instead of that, try operator, whatever, you can just say 1 minus the number. 1 minus 0 is 1, 1 minus 1 is 0. It's just simpler. Otherwise, I guess that's fine. The thing is, he's rewriting these strings every time. Whereas what I did, I just appended to a list, so I'm never having to remake the list from scratch. So I think my dragon curve was actually more efficient than his, because every time he does s equals, he has to make a completely new string, because strings are immutable in Python, but my list is mutable. So I think my dragon curve is actually the better way of doing it. But otherwise, yeah. All right. When run, this program outputs. Okay, well, he didn't output anything. He actually tried to run this as well. Suppose he might be capable of doing that. Didn't work this time. All right, let's test his code. Let's check this against, so 1 0 0 1 0 1 1 0 0 1 0 0 1 1 1 1 0. Yeah, it's correct. All right, he'll get this for sure, but let's just make sure. He actually run the program. Okay. Now adjust for the following modification. Right, I mean, if he's, I don't even need to test his code. If he's given me the answer, that fits the, let's just make sure it's the correct answer. That fits the requirement. 011 0. No. That's not right, but his code might be right. I think he might be using an answer from someone else who's used ChatGPT before for this very same problem, and he's just assuming that that is what the answer. Because I don't think ChatGPT runs Python code to actually test it. I think he's actually just copying what someone else had. But they had a different input from me, because this website gives you different inputs, gives everyone different inputs. So he's given me the wrong... Okay, but it doesn't matter. We'll test his code. That's what matters. Yeah, that happens sometimes. He gets a bit too cocky sometimes. All right, that's what he's given us. Let me check if that's right. 011 010 111 011 00011. Yep, it's fine. ChatGPT wins again. All right, should I do another one? I think I have time for another one. Let me have a look at the stats. Let's see, is 17 going to be a hard one? Ooh, looks like it is a hard one. I'll probably still do it within the hour. Okay, let's have a go. It looks like a breadth first search type thing through a grid. I'm normally good at those, so... Okay. 2 steps forward. You're trying to access a secure vault protected by a 4x4 grid of small rooms connected by doors. You start in the top left room, marked S. You can access the vault, marked V, once you reach the bottom right room. Okay. So these walls are hash. These are doors. The doors in your current room are either open or closed. Unlocked based on the hexadecimal MD5 hash of a passcode, your puzzle input, followed by a sequence of uppercase characters representing the path you have taken so far. Okay. So basically, the locked status of a door. Ooh. So breadth first search might not be the answer here. The path you take to a door determines whether that door will be open or not. Completely different path to a door will yield an independent result of whether that door is locked or not. Interesting. Are we allowed to revisit rooms? If we are, that makes it even more complicated. So, okay, let's just read. So, you take the MD5 hash of the path you've taken so far. You take the first 4 characters of your hash. Any B, C, D, E, or F means it's open. Anything else means it's closed. So basically, you've got a 5 in 16 chance of it being open. Roughly 1 in 3. So you're kind of gonna have to... It's less than half a chance, so you kind of have to go back and forth a bit to get these doors open. Oh, okay. All you need to do is reach the bottom right room. Reaching this room opens the vault and all doors in the maze. Okay, I get how this works. I don't need to read all this. Passcodes actually used by Easter Bunny Vault Security do allow access to the vault if you know the right path. For example, if your passcode were that, the shortest path would be that. Okay, we can test. These are some good test examples we can test. Shortest path to reach the vault. Alright, DJ. Have a good sleep. Oh well, this is an ugly problem. It's okay, we can't really use breadth first. Well, we sort of can, but okay, you're allowed to go back and forth between nodes. So neighboring states are... So a state is a position you're in coupled with the path you took to get there. So we can still find neighboring states. But we'll never repeat states. If you take a different path to get somewhere, you'll never have the same... You'll never have two states. There's never two ways to get to the same state. Because they each have unique paths. Okay. So we do breadth first search amongst states where I'm considering the path, the full path. Okay. When I phrase it like that, it doesn't sound too hard. You just have to couple the path with it, which won't take up too much space, I guess, as long as you're not dealing with like thousands of characters. We just stop as soon as we get to room. Okay. It's 4x4. Interesting. All right. And we're at 0, 0, and we need to get to 3, 3. Oh, I feel like this is not. Let's think. There might be a more efficient way of doing this. It's more of a dynamic programming problem. Let's think about it. We want to get to the goal. To get to the goal, we had to have come from here or here and had this door open or this door open, respectively. So we're trying to find the shortest path to this room with this door open, or the shortest path to this room with this door open. And then that works backwards. So to get to this, the shortest path to this room with this door open is the shortest path to this room with, oh no, but the MD5 hash. No, forget what I said. We have to store the entire path. So I will have to do the state space thing. There's no shortcuts here because the MD5 hash will be unique. All right. Okay. Let's start coding then. I think I can do this. Also, let me just change this. We're on 17 now. Okay. So we've not been using input.text much these days. All right, so we got puzzle input, passcode. All right. Passcode equals that. So okay, let's define a state then. State. No, it's a class. Class state. So it would have a position, as an X value, a Y value, and a path. Okay. Yeah, okay. Get neighbors. Given a state, we want to find where its neighbors are. And this is where we factor in the MD5 stuff. So let's take, we need to use one of the previous problems I did this. Where was it? It was 14. All right, we got hashlib.md5. All right. So we take the MD5 hash of so it's the pass code plus, so the path will be a string of ups and downs, lefts and rights. So let's say the path. We have to encode that. Okay. H equals that. So H is a hash. But we just take the first 5 characters. So am I matching this so far? First 4 characters even. And that represents the up, down, left, right. All right. So deltas equals this. So this is the set of plus or minus 1 values we add to x or y. So we go through each of these characters in the hash, and that'll tell us if the door above is open, and that'll give us a delta to add to this list of deltas. So if H0 is in, what was it? B, C, D, E, or F. B, C, D, E, or F. Then the door is open. So if it's H0, that means we can go up. So that means we don't need deltas. Get rid of that. Okay, so the new x equals, so we go up, so x doesn't change, equals the old x. The new, let's just say new x, new y equals self dot x, self dot y minus 1. If we're within the bounds, so this is equal to, it's less than or equal to less than 4, and 0 is less than or equal to new y is less than 4. So we're still in bounds. Then up, we yield a new state who has new x, new y, and then the path will be the old path plus the character, so it's lowercase. No, it's uppercase. Now we copy this for each. So H1 is... Where did they list these? Up, down, left, right. Okay, up. So this is down. So it'll be +1. New X, new Y, self-delete. Down. So this one will be up, down, so it'll be left. So it'll be X -1. Y will stay the same. So left. Alright, this is looking nice and clean actually. It's not that complicated. H3 in B, C, D, E, F. Anyways. This one will be +1. And that'll be right. So that's... It looks a bit weird, but... That gets us the neighbors. Anything else? Okay, so... We need to be able to hash... Hang on. What are we going to do with this? We're going to put it into... We're going to do breadth first search. So we need to put things into a queue. No, we don't need to... Yeah, this is fine. Right. Okay. Define breadth first search given a start and a goal. Q equals... do depth first search. We don't even need to use a queue data structure. We're finding the shortest... No, it has to be breadth first. If we want the shortest one, it has to be breadth first search. Q, so we want to import... Q, import... Q... So Q equals Q. Q dot put... state... start dot x... No, start... the x value, which will be the first, so the start will be a pair. Start 1, and then we need the path, which is just an empty string. Q dot put. Okay, that's all we need. While not Q dot empty. Current equals Q dot get. All right. Now, what ultimately what do we want? We want the... We actually want the full path. Interesting. Okay, fine. If current dot we can do this in the neighbor check. So current equals q dot get. All right. So, for neighbor in current dot get neighbors. So we get a neighbor state. We just put it in the queue. Queue.put neighbor. That is BFS, except we haven't got the goal check. So the goal check goes here. If neighbor dot x neighbor dot y is the goal, return neighbor dot path. Otherwise we keep going. It's a very short BFS because you don't need to keep a hash map. You can never reach the same state twice by two different paths. Because of the way... In theory you can, but it's so phenomenally unlikely because it's MD5, so we would assume you can't. Okay. Start equals 0, 0. Goal equals 3, 3. Print BFS start goal. All right. What's the first problem? Okay, we didn't hex digest. We didn't hex digest. I don't even understand what that word means, hex digest, but we didn't hex digest. I'm trying to make a joke saying that's when I eat or something. I can't think of a funny one. All right. Dud. Dudderulurudura. Okay, is that the answer? That was quick. It's correct. I thought it might be a longer path, but... I mean, okay. Every time you take a step, it's kind of 1 in 3 chance for each door to be open. So you're gonna wait around, like kind of like you have to revisit a node like 3 times before the door you want is open, roughly. So it'd be sort of like the length times 3. Sounds about right. Okay, part 2. You're curious how robust this security solution really is, and so you decide to find longer and longer paths which still provide access to the vault. You remember that paths always end the first time they reach the bottom right room. What is the length of the longest path that reaches the vault? What the heck? Why is there even a longest? Why is it not possible to... It's 1 in 3. So you can't have infinite cycles. But can you? No, you can't, because at some... Fine. There exists a longest path, We need to find it. So what do we do now? How do you normally find longest paths? I don't often do this. I think we have to go through all paths. We can't skip any. So basically, we have to do this again. But we keep track of the longest path. Every time we get to a goal, we don't take any neighbors. Right? Hang on, so So we want to keep track of max length equals 0. Right. So we get a current node. All right, so if we've reached the goal, then we, instead of returning the path, we put max length equals max length neighbor path. So we update the new maximum. But what's very important is we don't put the goal state back into the queue. So we run this till we run out of nodes. So we've gone through every possible path. All the ones where we hit 3-3, the goal, we've taken the length of the path. So after we've done that, I don't know how long that's going to take. It could take a long time. Return max length. Max length. Max length neighbor.path. That should be length neighbor path. Seven, 8, 8? That was quick. What? Okay. I just assumed it would take a long time because you have to close every path, so... Hello? Is that Mandarin? Mandarin name? Welcome to the stream. Oh, it says an English name next to it. HC Yang. Are you familiar with Advent of Code? Right, so let's check if this is correct. 788. Yes! So that wasn't actually a hard problem. It was... You just do BFS, but you've got to be aware of your state space. It's not the traditional state space where you're sitting on a position. Here, you're sitting on a position and you're remembering the path you've taken there. So the branch factor is high and you never visit a state you visited before in a different path. But aside from that, in principle, it's the same algorithm. You just do breadth first search as normal. The longest path, just try all paths. Well, okay, here's the problem. 16, we have to just copy that in. No, it's 17. Let me just finish this one. So given your vault's passcode, okay. I need to give the puzzle input here. Okay, ChatGPT has, of course, probably solved the problem. Let's see. His BFS is quite bulky compared to mine, but it's... Oh, because he's baked all the direction stuff into the BFS rather than separating it. Okay, that's fine. Yep, it looks correct. And then you start 0, 0. Same algorithm that I did. All right, let's test it then. So during the pandemic, were you staying in Taiwan? Because I heard that Taiwan was actually the best country in the world at protecting against the pandemic. I was in Thailand, which was, I would say, like the second or third best country at avoiding the pandemic. But I think Taiwan was slightly better. Let's put this, make a new file. Run. So we got dud, roll, rudder. All right, does that match? Dud, roll, rudder. Yep, that's correct. And now we have to adjust for the longest. All right, see if he can do it. So he's now trying to find the longest path. Thank you. However, lots of people in Taiwan think the other way, Ghost Island, if you transit. So what, you're saying it was very quiet and boring? But I mean, like, things were still open, weren't they? In most of the world, all the shops and the restaurants and everything was closed and everyone had to stay at home. But I think in Taiwan, you were still able to actually go out, so that's what I mean. It was the same in Thailand. I was in Thailand and everything was still open. Like nightclubs and discos were still open, cafes, restaurants, everything was still open. Everything was normal during the pandemic. I think maybe we had like 1 or 2 weeks where we had to stay home, but the rest of the year was fine. And I think in Taiwan it was the same for you, wasn't it? But everywhere else in the world, everything was closed, so we were the lucky ones. We could live a normal life. Yeah, and I never even caught COVID. To date, I've never had the disease. I don't know what it feels like. Because I stayed in Thailand where it was very rare to catch it. And whenever people did catch it, they isolated them very quickly and efficiently. Which I think is the same in Taiwan. And like New Zealand as well. I think New Zealand was also very good at containing outbreaks. But my nationality country, England, was terrible. Absolute disaster. Alright, let's just run this. Which is why I avoided going to England during the pandemic. Alright, this takes a long time to run. That's a problem. It shouldn't take this long. So it looks like he's got an infinite loop. But his code looks the same as mine. So while Q. You don't need to use breadth first search. He's using depth first search because either way you store the path, so you don't need to use breadth first search. Interesting. I didn't think of that. So this is actually less overhead because you don't need to use a queue data structure, but the complexity is still similar. Alright, this is an infinite loop, so let's see. Stuck in an infinite loop. Can you fix it? Okay, he doesn't get it. All right. If you click on the actual code, you can provide feedback. I think that tells him what you want. Oh, okay. He's stuck. He's stuck trying to. I think sometimes ChatGPT just freezes because lots of people are using it. It's so popular now. It's one of the most popular websites on the internet. So they get lots of network errors. Let's refresh the website. I don't know. I think the website's just hanging. Let's try regenerating this. He's dead. ChatGPT is dead. I think the site is down, maybe. Well, that... I guess... it's inconclusive then. We'll have to... Unless the site starts working again, I guess I should just end it there, and next stream I'll try it. Using ChatGPT to learn programming is really a great new route for the ones... Yeah, exactly, because it explains... You'd have thought some AIs will just give you the code, but it actually explains what the code does. So it's... What's the word that's used in machine learning? It's interpretable. Because often you have machine learning models which are not interpretable. They just give you the right answer, but they don't know how they got the answer. But ChatGPT is interpretable, so it actually knows how it got the answer and it explains it to you in natural language. That is I didn't expect that it would do that. So yeah, the site is broken. Alright, it's working now. We can try it. Opposite direction. Interesting. Why would you need to know the opposite direction? It's stuck. I think there's still network errors. Oh, he's done it. Okay. He thinks the problem was that... No, that's not the problem. The problem was the exact opposite, that you weren't terminating at all. Alright, whatever. Copy code. Ah! He hasn't printed anything. There's no print statement. He forgot to add a print statement. Okay, but there is no print statement for the answer. You can print the result by adding print ands at the end of the code. Yeah, you do that, ChatGPT. What am I hiring you for? I'm not going to code it myself. Okay. Seven, 8, 8. That's correct. Alright, it took a couple of failed attempts, but he did actually solve it faster than me, so... That's another win for the ChatGPT. Let me update the scoreboard. Hextree 3, ChatGPT 14. And with that, I think I'm done for today. That was 3 problems done. 15, 16, and 17. So... we are at... That one people found quite difficult, apparently. but the next 3 are reasonably easy, and then it gets a little hard, maybe? We'll see. So, for that one, that problem, I'll have leaderboard 17. The fastest solver was Kevin Wong at 8 minutes 20. No, yeah, 8 minutes 22. He solved both stars in 8 minutes 22. That's believable, actually, because it's BFS. As long as you know it's BFS, you probably can code it quite quickly. And so yeah, okay. How long did I take? Probably like 15 minutes. I probably could have got into the top 100, actually. I would say 15 to 20 minutes. With ChatGPT, I would have been first. That's the problem. Next year, this coming December is going to be a disaster because the top 100 people will all be ChatGPT. They won't even be coders. There'll be people who don't know coding. They'll just copy the problem into the ChatGPT and it will solve it within seconds. So this December is going to be interesting. I mean, this December the leaderboard's not going to mean anything, is it? I don't do it for the leaderboard. I just do it for the fun because I don't get into the leaderboard anyway. But all right, that's enough coding for today. I used ChatGPT for game programming recently. It really helped a lot and is a very efficient way for coding. Yeah, I can believe that because there's a lot of patterns in game coding that a lot of people are using. So ChatGPT trains on all of those and it recognizes it. So it knows all the Unity or Godot or all the engines. It knows the patterns people use pretty well. So I think game programming in particular, it's going to be very strong in. Because there's a lot of repetition between codes, people writing code for, physics or writing basic AI code and stuff like that. Oh, you're using Unity and C#. Yeah, I've had a go at Unity and C#. Yeah. I've seen YouTube videos of people that made games entirely using ChatGPT, like making Flappy Bird, but never coding themselves, just using ChatGPT, and it works. You can do it. All right, well, thanks for watching, HC Yang and the others who are here, Diaj and Rabbits, Mugurelius, and I will probably be back on, probably not tomorrow, but maybe the day after, with some more of these problems. I've got several years to get through before December. All right. See you next time.